All right, time for paper breakdown. So let's go straight into the questions. First things first, we have a acid-base equilibrium titration curve question. This is a lactic acid. I'm just going to be using Ha to denote it from now on so that it's easier. This is the conjugate base A minus. We know that when we mix both of these species in the same solution, we call that a buffer. So we create a buffer first. And that's actually our initial pH of 3.25. This is the pH of the buffer consisting these two species. How much is there inside? We have no idea. So we are actually performing a titration on the buffer, which is not usually what we see. The reason why this first question is difficult is because in a normal titration curve, we usually start at the beginning with only one species like an acid. And then only at the equivalence point, we have totally neutralized the acid into its conjugate base A minus. In a normal titration curve like this, the maximum buffer occurs exactly at halfway of the equivalence point. So if you add 20 cm cube for equivalence, then you only need 10 cm cube for the MBC. Halfway of the equivalence, that is. But this question, you don't see that happening. In this question, when you add 3x of sodium hydroxide, you already attain the MBC. The equivalence point is after you add 8x. Now, a lot of you guys would think if this is 8x, that means the half equivalence will be 4x. Yes. And you would think that 4x is the MBC, but no, that's not the case here because at the very beginning, we're already starting with two species. Normally, we start with one, so that's why all these rules like half equivalence is MBC will hold. But here, if you already have both species present, things will start to become a little bit different. So let's go over to the questions now. Okay, so first question, pretty simple. Explain why the pH at the equivalence point is above 7. Now, always remember, at the equivalence point, you only contain the salt. The acid will definitely be fully neutralized by this point, so we only have the salt, which is A minus. This salt will undergo hydrolysis. So the equation will be your salt hydrolysis equation. Our salt is this, react with water. Salt hydrolysis is always reversible to give you back the acid, and then at the same time, you produce OH minus. Because OH minus is produced from hydrolysis, the concentration of OH minus will now be higher than that of H plus. So now the solution is overall basic. pH is more than 7. So that's our full answer for question 1. Part A. Okay, let's look at part B. So now we need to show that the ratio of the acid and the conjugate base, I'm just going to use HA and A minus to represent them from now on. You need to show that it's 4:1 in the original buffer solution. Now, do take note, we started off with a buffer already. The titration curve began with a buffer. We are supposed to prove that at this starting point, this buffer contains 4 times more acid than conjugate base. How are we meant to prove that with such little information? We only know the initial pH. We don't even know the pKa or the Ka of lactic acid. And we don't even know what these exact amounts are. Man, what are we going to do here? Okay, so there are a couple of things we need to understand first. At MBC, you must remember the concentration of both acid and conjugate base is equal. Bear that in mind as we go into the working. Now, what about the equivalence point? At the equivalence point, there's no more acid. All of it has been neutralized by NaOH, and all of it now turns into A minus. That is point number 2. Bring these 2 points into the question's answer right now. Okay? Next thing. So basically, our goal here, right, is to do this. We know at this point, 2 species are equal. Then when they add another 5x more NaOH, then all the acid is now gone. Let's do that again. Okay? Now, we're going to draw some tables. And in these tables that you're about to see, they will all be calculated in number of moles, amount. That's because that's the most reliable way of calculating this. If you calculate this in concentration, it's going to be quite complicated because the volume constantly changes here. We even know the concentration of NaOH, so we can use that to our advantage. Okay, so let's go over to our answers here. Okay, so in this case, we are trying to find the original buffer's proportion of these 2 species. Okay, first things first, when they add 3x of NaOH, we get an MBC. MBC means these 2 species are equal. Okay, since we have no idea how much acid and conjugate base there is in the original buffer, I'm going to let A be the amount of acid in the original buffer, and B be the number of moles of conjugate base in the original buffer. So this is my initial. I'm going to add 0.003x moles of NaOH. Now, where do I get 0.003x? The volume is 3x cm cube. The concentration is 1 mole per dm cube. So I can just take 1 divided by 1000 multiplied by 3x. So that gives me 0.003x. Okay, I'm missing all the x here. Let me just quickly add that in first. Okay, so, right. Once we have this, now we know that when you have MBC, there's only 2 species, acid and conjugate base. This means the OH minus that you added, right, must be completely removed. So we'll be left with 0. I'm going to minus this here. I'm going to be minusing this on the left side as well. On the right hand side, I'm going to plus that amount because they're all 1-to-1 ratio. So this will reach 0. This one, I'll just take A minus this value. This one, I'll take B plus this value. Now, as we mentioned just now, these 2 species are equal at this point. This must be equal to this. So we can create somewhat like a equation, right? Okay, I'm going to bring all the numbers to one side, the alphabets to the other side. So A minus B equals to 0.006x. That is like the first equation. We're kind of doing like a simultaneous equation here because I already told you guys the second point is this. When you add until 8x, right? At the equivalence point, you only have this. You don't have any more acid. Okay, so from this point, we add another 5x more NaOH. We add another 5x more NaOH. Okay, so we're going to draw another table. When another 5x cm cube of NaOH is added, all the acid now turns into A minus. So I'm going to continue off this point over here. So I'm going to place that under the initial value. Let me add the x's in. I forgot about that. Okay, I'm going to continue this value here. I'm going to continue this value here. So when another 0.005x of NaOH is added, this will definitely minus off, right? Because at the equivalence point, I only have A minus. So this has to be 0. Okay, I'm going to minus this value as well. So to give you this. And I'm going to plus it on the other side. Okay, to give me this. Remember, at the equivalence point, there's no more HA. That means this is equal to 0. So I can use this to find the value of A. A is basically 0.008x. Now, can I use that to now find B? Yes, because based on our simultaneous equation from earlier, A minus B is this. So that means B must be 0.002x. Now, the x doesn't matter here because we're trying to find the ratio. So A represents the acid, B represents the conjugate base, A is to B, gives us a ratio of 4:1. Now, I have made it very detailed over here, okay, because this is a show question, and show questions have to have a lot of working involved. This is the question that is perhaps the most difficult in the entire paper, and under time conditions, you guys will probably struggle to think of this answer. Okay, but yeah, that's for part B. Let's look at part C. So determine the acid dissociation constant. Now, in an exam scenario, when they give you the answer to a question, basically they say show that something is 4:1. You can actually use this, right, to actually move on. Use that value to move on to the next few parts so that you can at least still solve for the next few parts. Difficult questions, they usually like to put it as a show question so that you can move on. Right? So we know that the acid and the conjugate base exist in a 4:1 ratio. And since this is a buffer, we can use this buffer equation. The initial pH is 3.25. This is sub in properly. So it's A minus on top, HA at the bottom. So this is a 1:4 ratio. Okay, so go and solve for this question. pKa is this value, but they want Ka, so go and take 10 to the power of negative that value to give you this. Okay, just go and write the units as well. Ka is always mole per dm cube, just like Kb. Right, go over the part D, explain in terms of POE. So you need to measure POE shift to the left or right in your answer. Explain why the slope of the graph only changes gradually over pH 3 to 5. Go back to the graph. 3 to 5 is like somewhere here. Now, the reason why it changes gradually is, as we all know, buffer. The whole point of a buffer is to resist the pH change. That's why the pH change is very gradual. Okay, so our goal here is basically to explain how the buffer works. Okay, but we need to do it in terms of POE lah. So we need to come up with an equilibrium equation first. Since the buffer involves these 2 species, I'm going to be writing an equation consisting of the acid and the conjugate base. Alright, then it will dissociate into H+. Alright. Now, when you go from pH 3 to 5, you're adding NaOH, right? So when NaOH is added, the concentration of OH minus goes up. When OH minus goes up, it will neutralize the H plus, causing the H plus to fall. When H plus falls, POE now shifts to the right. So when you shift to the right, it actually offsets the drop in H plus, right? So again, when OH minus goes up because you add NaOH, this guy goes down at the start. But POE will now shift to the right to offset that decrease. So he will increase it back. So overall, is there a very large net change? No. This one drop, this one increase, right? The change is kind of like balanced out. Not completely balanced out, of course, because remember, position of equilibrium shifting only offsets it partially. So you will not offset it totally. If it offsets the change in H plus totally, that means the pH will never change. It will stay completely still. It will be completely constant. But we know buffers don't work like that. When NaOH is added, the pH still increases just to a very small extent because, again, when the H plus initially drops, the POE shifts right, causing H plus to increase, but not as much. Overall, there's still a little drop over here. But the point here being, because the change is very small, the pH remains relatively constant. Don't write constant only, you must use the word relatively inside. Okay, because eventually, at the end of the day, there's still a change. Okay, so that's our answer here. Right, moving on to question 2. Question 2 is on solubility equilibrium. You can tell instantly because of the word KSP, and you can tell this is going to be a selective precipitation question. So we have Cl minus and Br minus in the same mixture. The only way to separate them is to add Ag plus in this case. Until the first trace of precipitate is seen. Now, precipitate is first seen when IP equals to KSP, so we have to do two calculations. Do the same calculation for AgCl and AgBr. What are we trying to calculate? We must calculate what is the minimum concentration of silver plus ions we need to add in order to precipitate each salt. The minimum concentration is where IP is equal to the KSP. So I make Ag plus the subject. Take your KSP, divide by the concentration of Cl minus in the mixture. This is the concentration of Ag plus that I minimally need to add, right, to see a trace of AgCl precipitate. This is the concentration I need to add to see a little bit of AgBr come out. Since this is a smaller value than this, it means, right, AgBr will precipitate first. So how do you show that it's the first to form? You need to give me the statement. Since the minimum concentration to precipitate AgBr is smaller than the minimum concentration to precipitate AgCl, then you can say it precipitates first. This part of the statement, this part of the statement here is very important. Moving on. So we're going to add silver nitrate until AgCl starts to precipitate. Okay, so think about it this way. I have drawn this diagram here. AgBr precipitates first because the concentration of Ag plus to add is much lower. To precipitate AgCl, the concentration is much higher. Okay, so with that said, that means this is the start of our precipitation. This is where we start to see AgBr come out, not AgCl. We're going to keep adding to precipitate more and more AgBr, but eventually we have to stop here at this point. Because if you add more Ag plus beyond this point, both will precipitate and you can't separate them anymore. It's just a mixture of solids. Now there's no way to separate it. You have to stop right before this point. So this is the end point. This is the start point. They want us to find out how much Br minus is remaining in the solution, because if AgBr is the one getting precipitated out throughout this entire journey, that means Br minus concentration will fall. We started off with 0.15 mole per dm cube of Br minus. How much is there left? It's going to be a lot smaller, and that's what we are trying to find. Cl minus never precipitated throughout this entire journey here, so that means the concentration of Cl minus stays the same in both cases. So to find Br minus at the end, we need to use values that are all at the end, no more at the start. So go and find the KSP of AgBr, because that is the only one with Br minus in our expression. To find Br minus, take the KSP divided by our Ag plus. Ag plus at the end. So go to your end, your Ag plus is this value, put this inside, you can get this as our concentration. So that means we can complete our diagram here. Concentration of Br minus left in the solution is 2.05 times 10 to the power minus 4, which is a lot smaller than what we started with. So we can roughly see that the precipitation was rather efficient, was rather effective. Okay, next portion here. calculate the percentage precipitated out. Okay, so this is how much there's left inside. So I found out how much is left inside. Then I just need to take 100% minus that percentage. This is how much they actually got out of the solution. 99.9%. If 99.9% has been removed from the solution, this is definitely a effective separation. So just make a conclusion like this. Okay, so selective precipitation done. Okay, we have this next part here which uses a different cation. Instead of using Ag+, they decided to use this thallium plus ion, right? These are the KSPs of each ion, and now they ask, will this give you a more or less effective separation compared to adding silver plus ion instead? What does it mean to have a more or less effective separation? Basically this. A more effective separation means the percentage that precipitated out is a lot higher. That's an effective separation. A separation that's not effective means maybe the percentage that actually got out of the mixture is like what, 70%, 80%. That's not an effective separation. So we are not given any numbers here. I mean, we are, okay, but you are definitely not going to be calculating anything just for a 1 mark question. This is purely qualitative. Okay, here's the thing. Effective separation only comes about when the distance between the start and the end point is as big as possible. Think of it this way. If you separate only a little bit, right, and then you reach the end point already, that means the gap is very small. You're not going to precipitate much out. But if the gap is very, very big, that means you can precipitate a lot of the ions out before you're forced to stop over here. So that means the larger the gap, the better. 10 to the power of minus 12, 10 to the power of minus 9 is 1,000 order of magnitude apart. Right? This is 1,000 times the difference. That's pretty good. You can tell from the KSP as well. Why we can compare the KSP straight up is because AgCl, AgBr, both of them have only 2 concentration terms. We can compare 10 to the power minus 10, 10 to the power minus 13. This is 1,000 times apart, which gave quite an effective separation. Will we get something as effective in this thallium situation here? 10 to the power of minus 4, 10 to the power of minus 6 is only about 100 times the difference. This was 1,000 times the difference. So you can see, you are going to expect the gap between the start and the end to be a lot smaller for this situation here. If the gap is a lot smaller, that means you precipitate a bit, then oops, we need to stop here already. So that means you didn't manage to precipitate a lot out. That means this is going to be a less effective separation. How do we put it into words? It's all about the difference in magnitude. Okay, the difference in between KSP of thallium chloride and thallium bromide is smaller than the difference between that of AgCl and AgBr. 100 times versus 1,000 times. This will result in a smaller percentage of Br minus ions being precipitated out. So that's why the separation is less effective. It might be only 1 mark, but this is how much you need to write for this 1 mark. Okay? Right, so now we're moving on to organic chem. Question 3 is pretty easy. Okay, so this is your electrophilic substitution, right? We are asked to draw like a part of the mechanism. Okay, so they ask for one thing you need to note: displayed structure of the electrophile. Now, what's the electrophile is clearly NO2 plus. Right now, how do we draw NO2 plus's displayed formula? Normally, we just draw this, right? We get it over and done with. Okay, but let's draw the dot and cross first. Okay, so ONO plus means you remove an electron from the less electronegative atom. So nitrogen is less electronegative. It used to have 5 valence, now it has 4. Okay, oxygen has 6 valence still. Now we settle the side atoms first. So oxygen here has 6 electrons, 6 valence. So you can form 2 bonds. 2 bonds here, 2 bonds here. Okay, fill up all the valence. Nitrogen has 4 valence. So yeah, that's pretty much it. In total, after bonding twice, it has 8 electrons. Nitrogen is the one bearing the plus charge, right? Because nitrogen got his electron removed, not oxygen. So when you draw out your displayed structure, double bond here, okay? And then there's a plus charge over here. Okay, by right, this shouldn't be bent like this because there is no there is no lone pair on this nitrogen. So by right, it should just be a linear shape like that. 2 bond pairs and no lone pairs. So there's a positive charge on this end. Okay, so now we need to draw the rich benzene ring attacking this poor nitrogen. So that's why it forms a bond here. The ring breaks with a plus charge, the hydrogen is still there. Eventually, the H plus comes out. Why? Because this bond will break and flow back into the benzene. So now the benzene is sort of like repaired, right? The broken ring is now restored, and then the H comes out as H plus because he lost electrons. When you lose electrons, you get H plus, right? So that's what we have for part A. Part B, why does the benzene ring form a bond with nitrogen atom? Why nitrogen? Because clearly nitrogen bears the positive charge. It is poor. So this is rich, this is poor. Rich always attacks poor, right? So you mention that in words. The nitrogen in NO2 plus bears the plus charge. So the rich pi electron cloud of benzene attacks the electron poor or electron deficient nitrogen, hence they form a covalent bond. Make it as detailed as this to secure the 1 mark. Last but not least, we have question 4. Okay, so some mechanisms to draw first. Okay, we are given a halogenoalkane, and then we have like this nucleophile here. Okay, yeah, just draw a mechanism. So this nucleophile clearly swapped out with the halogen, and we know halogen alkanes, right? Your Rx only undergoes nucleophilic sub, but you need to consider whether it's SN2 or SN1. This is a primary Rx. Primary Rx tends to favor SN2. So they never say anything else in this question, so you can rely on this assumption that primary tends to undergo SN2. This is how you draw the mechanism here, nothing too crazy. Some things to take note of. Please make sure your slow and fast are there. Please make sure that the nucleophile attacks from the back. Must be like this because it's called rear side attack. Partial charges are there. Please make sure when you draw the transition state, you label it, and at the same time, the overall charge of the transition state here is plus because you are introducing overall charge of the transition state here is minus because you are introducing a negatively charged species onto the compound. All right. Then finally, this bond breaks, and then the whole stereochemical formula is inverted. Right now, it flips to the other side. See how these three are leaning to the left. Now all three are leaning to the right. Okay, and then from there, the Cl minus breaks, and then you form Cl minus. That's your fast. Okay, actually, we shouldn't be writing fast here. I've told you guys this before. Little mistake there. Okay, you should just be writing slow, and that's about it. Because, right, SN2 is considered a one-step reaction. One-step reaction, so you just have one slow step, and then it kind of like seamlessly goes to the end. Because we have said before, transition states are purely theoretical. They don't actually exist. So we just treat it as if this goes to here straight away. So it's just one step, slow. All right, so just remove the fast if you have it. Okay, next up, okay, let's take a look at part B, another mechanism drawing question. Now they give you instructions to draw. If they give you instructions, right, that means it's a mechanism that you have not really seen before. So you just need to follow the instructions, apply what you know, get the answer. Okay, so we have this, and then clearly the Br and 1H is gone. So this is actually our elimination. We are not taught the mechanism for elimination, so they're going to teach us here. So CBr bond breaks heterolytically. Okay, they give a carbocation and a bromide. So it's like SN1 like that, right? So the bond just breaks without any nucleophile attacking. Please draw the partial charges. Bond breaking is always slow, so just add it in. Okay, you form carbocation and Br minus. Okay, next thing is this. After the Br is gone, the H must be gone as well. Elimination gets rid of the HBr. So how is the H gone? This ion over here, CH3CH2O minus, will remove the hydrogen because rich attacks poor. So I need to see the lone pair on the O attacking this poor hydrogen over here. And when that happens, you'll form this alcohol here. At the same time, they said this CH bond will break. Okay, and the CH bond breaks. Where do the electrons go? The electrons, right, will now have to form this pi bond over here. So you have to point towards the bond. Do not point towards the carbon with the plus charge. I understand rich attacks poor, but from now on, whenever you see a new bond being formed, especially a pi bond, point to the current bond first. Okay, so that's how you form that pi bond here, and the alcohol is also produced. Now, don't draw any partial charges on this H because C and H, right, don't actually have partial charges. It's a non-polar bond. The O minus just steals the H, so just do it. Just attack it, and that's it. Okay, you can write fast step over here as well. Okay, so, right. Okay, no name for this reaction because you have not learned this before. Okay, right. Question 5 is an elucidation. As I said, that's why this paper is difficult, right? It's not really because of the individual questions itself, apart from question 1. It's because of the time management. Okay. Anyways, yeah, let's run through every one of these deductions here. Violet complex with neutral FeCl3 only points to a phenol. Now, as we go along, right, one tip that you can do for elucidation is always check with the oxygen atoms. We have 2 oxygens here. One of the oxygens clearly belong to the phenol. Our goal now is to figure out what the other oxygen is. It definitely can't be a carboxylic acid, right? Because carboxylic acid has two oxygens, for example. So we know one is phenol, the other one is something else. I2NaOH and heat to give yellow precipitate. This is our classic oxidation reaction. This oxidation reaction implies J has either methyl alcohol or methyl ketone. Methyl alcohol, so we draw it out, or methyl ketone. We will try to narrow it down later on. Okay, both are now seemingly possible because the one more oxygen can be either your alcohol or ketone. So yeah, does not decolorize bromine aqueous. There are only three functional groups that can react with aqueous bromine: alkene, phenol, and phenylamine. Can't be phenylamine here because there's no nitrogen in the compound. Can't be alkene because they say doesn't decolorize. So you can say J does not have alkene. Great. More information. If it doesn't decolorize bromine, does that tell you there's no phenol? Wait, we just said there's phenol. We know for sure there's a phenol. Shouldn't phenol undergo reaction with Br2 aqueous? Right? Because we got learned before, right? Phenol will react with Br2 aqueous to form this tri-substituted product. Okay, it substitutes on the 2,4,6 position right here. Okay, you can't see it. Let me just move it down. It forms this product. What? If it doesn't decolorize, that means the phenol doesn't react with Br2 aqueous. This can only mean one thing. This can only mean that the 2,4,6 positions on the benzene are already occupied. They're already occupied by something else. So for example, if the 2,4,6 positions are occupied by other random crap like NO2, maybe a Cl, maybe like an alkyl chain over here, then Br cannot substitute at all. That's the only scenario where Br2 aqueous doesn't decolorize in phenol. This is ultra important. Go and take note because this allows you to determine your structure. Okay, dichromate, okay, to give you K. Okay, so we know that there is a benzene ring already because there's phenol. Don't need to worry about side chain oxidation because we are using dichromate here. So clearly something is getting oxidized. Now what gets oxidized? Okay, there's only two oxygens. One oxygen is phenol. Phenol can't oxidize. The next oxygen containing compound is either alcohol or ketone. Methyl alcohol or methyl ketone, right? It can't be ketone then because ketone cannot further oxidize. It has to be a methyl alcohol. So we can cross this out. It has to be a methyl alcohol in J. So you can write it down. Methyl alcohol in J oxidizes to methyl ketone in K. This is the only way that it can make sense. This is our oxidation reaction. You can state that as well. Last but not least, J with PCl3 to form compound L. They never tell us what compound L is, but at this point it's very clear. There is an alcohol in J and to turn into a chloroalkane in L. So that is our nucleophilic substitution. Nucleophilic substitution. So you just have to tell me that the methyl alcohol in J turns into chloroalkane in L. Chloroalkane. You can even draw it out if you want, like this. Or if you want to write in words, right, also can. A methyl alcohol is a secondary alcohol. It turns into a chloroalkane in L. Also can. You can even say secondary chloroalkane because it's the same structure, right? Okay, so many ways you can do this. Anyways, with that, we can get our structures. So the only structure that we have to get first is J. Okay, we can't get anything else yet because everything else comes from J. So your K and L stem from J. So we need to do two things. We need to first draw the benzene ring with our OH here. This is our phenol on compound J. And now you should always ask yourself, how many more carbons do I need to put? I have 10 carbons. 6 carbons already come in the form of benzene. That means you only need to play with another 4 carbons. Now look at this right here. We have to occupy all 3 2,4,6 positions. 4 carbons to occupy 3 positions. The only way to do this is 2-1-1, right? So we can put a 2 carbon side chain on position 2, 1 carbon here on position 4, 1 carbon here on position 6. What else do we need to add? We need to add a methyl alcohol in J. The methyl alcohol can only come here on the 2 carbon side chain. That's our answer. If you put the methyl alcohol over here on position 4, it's also fine because they never specify anything beyond that. They just tell you to occupy all 3 positions. So I'm just going to stick to this. Then compound K, right, you just oxidize the alcohol to ketone. So this is our answer here. Oxidize it to ketone. Remember, no side chain oxidation occurs with dichromate, so all of it stays. Okay, last but not least, we have the OH here turned into a Cl in L. So copy out the rest of the compound and just put the Cl over here. So again, if you guys put these 3 groups, right, onto the 4th position, it's also fine. Okay, and that's our final answer.